Hi there, Wes here with another calculus tutorial. Here we're doing question 3 from section 2.8 of John Stewart's calculus. Now, if you look here, this question is basically asking you to match the graph on the left to its antiderivative on the right. And so when I get a problem like this on a test, I think process of elimination. So the first thing I see is I see one of these graphs has straight lines, particularly B. B has straight lines, which means the derivative is going to be at a constant rate. So I expect to see flat lines in the derivative because over the first part, you can, if you look at the rise over run, you can see that the rise over run is going to be constant. It's going to be about 1.5 or so because it's a little bit longer rise than run. And I can say, okay, maybe this y section is about 1.5 or so. And then you can see the next section, it's negative. And look, it looks like it's underneath the x-axis, therefore it's negative. So you can kind of go, okay, there we go. We'll cross those two off. The next one I look at is C. Why do I look at C? Because I see that the slope is 0 at x equals 0, because the tangent line here, it's 0. If you need a little bit more explanation to this, go to the last video. But if I do the rise over run, I can go any length along the x-axis, and because there's no change in the y, the value of the derivative is always going to be 0. So we basically know that at x equals 0, y prime is going to be 0. So then when I look at the graphs here, right, I look at which graphs go at the 0 point is 0, and it's only 1 and 3. But I still have to eliminate it a little bit more, right? So if we look at the far corner here, so I put another dot on, we can see that the rate of change is slowly getting slower in C. So you'd expect the value of the derivative to slowly approach the 0 mark, right? But if you look at question 3, it kind of looks like, graph 3, it kind of looks like the derivative is getting faster and faster and faster. In fact, it's getting really large and really negative. Whereas the slope in the other one looks like it's getting very, very small. Like maybe if it's say 0.2 in change over this long x direction, then we could say that the rate of change at x equals 5 should be about 0.01. And if you look, which one of these two graphs at x equals 5 or at the end of the x looks closer to a very small number, it's obviously graph 1, right? You could say, yeah, maybe that's 0.01. So we definitely know it's not 3. Therefore, we can say that C matches with 1. So we'll knock those two off. Now we have two sets of graphs left, don't we? We have A and we have D, and two graphs to match it with. So I'm just going to bring up D at random. So with D, we can see that the derivative is 0 at 2 points right off the bat, right? So I'm going to draw, 3 points. I'm going to draw in the lines where the derivative goes to 0. You can tell it goes to 0 because no matter what distance you take in the x direction, there's no change in the y, right? And so we can see that this happens at, we'll say, x equals -1. That's just a rough estimate. X equals 0 and x equals 1. So when we look at the graph here, right, what we're expecting is that the graph is going to be 0 at these points. Now, if you look at graph 2, you can see it is 0 at about x equals -1, but at the 0 mark, it's way up maybe at like 3 or 4. And then if you look at the x equals 1, it's 0 again. But because it's not 0 in the middle, we can say it's not the second one, and it has to be the third one. Because when we check these 3 points here, you see it doesn't quite line up where you expect in number 2, but it lines up perfectly where we expect in number 3. Therefore, D is number 3. And now we can cross off that one as well. And by process of elimination, graph A must match up with number 2. And just to show you that, I just put the tangent lines on A and put the dots showing that the 0 marks match up, right? And there you go. If you have any more questions or you need any more help, feel free to let me know in the comments or if there's a specific problem you need solved. And as always, if you like, share, and subscribe, feel free.